The trail comes up damp underfoot, even on mornings without rain. In the Shenandoah, the soil holds moisture long after a storm has passed, drawing it up through layers of old leaf and root and decomposed stone until every step on an unpaved path has a slight give to it, a small yielding that is particular to these mountains and to no others. The air in the early hours carries the smell of that wetness, something green and mineral, the specific combination of oak and iron-bearing rock, and the slow exhalations of a woodland that has been doing this since before anyone was around to notice. Above the canopy, through gaps in the trees where a slope bends and the ridgeline becomes briefly visible, the Blue Ridge extends in both directions like something settled and permanent, a low continuous wave of forested height running from one edge of the visible world to the other. A park ranger walking a morning patrol in 1950 or 1960 or any time in the long middle stretch of the 20th century would have covered this ground at the pace the terrain required. Not fast, not urgent. The work of patrolling a national park on foot through mountain woodland is largely the work of being present and attentive, of noticing what has changed since the last pass, a downed tree, a trail that has washed out at its lower edge, the evidence of an animal having moved through in the night. The ranger carries whatever the morning requires, a pack, a radio in later years, a hat against the sun when the canopy opens. The boots are worn to the shape of the foot. The route is known well enough that the attention can go outward rather than down, to the light arriving over the ridge and the first birds calling from somewhere inside the green dark of the trees. Roy Sullivan walked routes like this one for the better part of 4 decades. He was born in February 1912 in Greene County, Virginia, which lies along the eastern edge of the Blue Ridge foothills, not far from where the mountains begin to ease themselves down toward the Piedmont. The county in those years was rural and sparsely settled, a landscape of small farms and timber and the particular self-reliance that comes from living at some distance from the places where things are arranged and decided. He would have grown up knowing the mountains the way that people grow up, knowing the ground they are born on, not as scenery, but as the actual weather and terrain of daily life. The ridges that tourists would later drive from considerable distances to see were for Sullivan and the people he grew up among simply the edges of the sky. He joined the National Park Service and began his career at Shenandoah National Park, where he would spend approximately 36 years as a ranger. The park runs along the spine of the Blue Ridge for some 70 miles, its higher elevations exposed to the full force of Appalachian weather systems that move through the region with particular frequency in summer. Anyone who has spent time in these mountains in July or August knows how quickly an afternoon can change, a clear morning giving way to building cumulus by midday, a first distant rumble by 2 o'clock, and by 3 or 4, a full storm with lightning walking across the ridgelines and the air smelling of ozone and wet rock. The Appalachians generate thunderstorm activity at a rate that is among the higher densities for any mountain system in the eastern United States, a fact that becomes relevant when the subject is a man who worked exposed mountain terrain for nearly 4 decades. Sullivan's first recorded strike came in 1942. She was inside a fire lookout tower during a severe thunderstorm, a structure designed to provide visibility across the forest canopy, which means it rises above the surrounding trees by design, placing anyone inside it considerably closer to the sky than to the ground. Lightning struck the tower. The bolt traveled through the structure, found its way down through Sullivan's leg, and exited through his big toe, burning a clean hole through the leather of his shoe. He lost the toenail of that toe entirely. He was, by the documented record, alive and ambulatory afterward. The tower had been struck, and a man had been in it, and the man had walked away, which is, medically speaking, not always what happens, and which is also, by almost any accounting, the kind of event a person would expect to stand as the most unusual thing that ever happened to him, did not stand as the most unusual thing that ever happened to him. 27 years passed. In August 1969, Sullivan was driving along a mountain road through the park on a routine patrol when lightning struck a nearby tree. The bolt deflected from the tree into the cab of his truck. His eyebrows were singed off entirely. He was knocked unconscious. The truck drifted to the edge of the road and stopped there, and Sullivan came back to consciousness in a stationary vehicle on the shoulder of a mountain road in the Blue Ridge, his eyebrows gone, the storm already moving on into the next valley. It is the kind of moment that is difficult to fully reconstruct from the outside, a man coming to in a stopped truck, realizing what has happened, and having to decide what to do with the information that this was now the second time. 2 strikes in 27 years. That interval, the long quiet decades between the tower in 1942 and the truck in 1969, is worth holding for a moment. A person who was struck once in a fire lookout in the early 1940s and then spent more than a quarter century working the same mountain terrain without further incident would have had every reason to treat the first event as a sealed thing, an anomaly belonging entirely to the past. The records do not say what Sullivan made of the second strike while sitting in that drifted truck, but they do suggest that from 1969 onward, the accumulation began to move more quickly. The Guinness Book of World Records eventually recognized Roy Sullivan as the person struck by lightning more times than any other human being in the documented historical record. This was not an informal recognition or a popular claim. It was a formal verification, the kind that requires producing evidence rather than simply asserting it. Medical records from multiple hospitals across multiple decades, Park Service incident documentation filed by Sullivan himself and by his colleagues over the long course of his career. Eyewitness accounts where they existed, collected and dated, and checked against the other records. The verification team would have had to sit with a considerable volume of paperwork, cross-referencing reports from 5 different decades, confirming that each documented event was genuinely separate and distinct, that the injuries described in the records were consistent with what lightning produces in a human body, and that the man named in each report was the same man. 7 separate strikes, each occurring in a different month and year, each leaving its own marks on the record. The probability of any one person surviving even a single direct strike is low enough that actuaries treat it as a negligible risk. 7 is a number that falls so far outside any reasonable probability distribution that it resists the usual frameworks for understanding coincidence. Sullivan continued working. This is one of the details that settles in when the full documented record is laid out. Not just that he survived, which was remarkable enough, but that he kept going back. He kept patrolling the ridgelines and the remote trail sections and the exposed mountain roads where Appalachian thunderstorms move through on summer afternoons, kept doing the work he had done since the beginning of his career, kept returning to the specific landscape that had struck him more times than any human being alive. There would have been practical reasons for this. The work was what he knew. The park was his terrain, the mountains his landscape, and a career of 36 years builds a kind of gravity that is not easily redirected. There may also have been something else, the particular stubbornness of a man who has been struck by lightning and has not been stopped by it, and who may have decided, somewhere in the long middle of his career, that stopping was not available to him. What the records report And what Sullivan told interviewers in his later years was that he had begun to believe the storms were seeking him deliberately. He did not describe this as a scientific claim or as something he could explain. He described it as a conviction that had grown alongside the accumulating strikes, a persistent feeling that deepened with each event and that stayed with him between events, during the clear days and the quiet patrols and the ordinary working weeks when nothing unusual happened, and the Blue Ridge was simply what it always was, wide, forested, still. He reportedly carried a can of water with him at all times, a precaution against the possibility that lightning might set his hair or clothing alight again. This detail comes from interviews and accounts gathered by journalists and researchers who spoke with Sullivan directly, and it is the kind of detail that lodges itself because it is both entirely practical and entirely poignant. It is what a person does after the fourth or fifth time they stop carrying the extraordinary separately from the ordinary, and they put the can of water on the seat next to them, and they start the truck, and they go. The Blue Ridge in Greene County looks much the same in any given morning as it has looked for a very long time. The tree cover changes slowly, the trails erode and are repaired, the lookout towers rust and are maintained or decommissioned, but the underlying shape of the land, the long ridges, the forest-filled valleys, the way the light moves across a slope in the early part of the day, remains consistent across decades and across the lifetimes of anyone working in it. Sullivan walked that landscape for close to 4 decades. He knew where the trail surfaces changed, where the drainage ran poorly after heavy rain, where the exposed sections of ridgeline left a person most open to what the sky was doing. He had the knowledge that accumulates in a person who has walked the same terrain for years and paid attention every time. It is worth sitting with that picture for a moment. The ranger on the morning route, boots on a damp trail, the ridgeline visible above the canopy in the particular early light of the Blue Ridge, the air still carrying its mineral and green smell from the night before. A man with 30-odd years of that trail in the soles of his boots, working a landscape he knew as well as any person could know it, carrying a small can of water on the seat of his truck because the sky had struck him more times than any human being in the documented record, and he had decided, practically and without apparent drama, to carry water. The fire lookout tower that held him in 1942 would have been a wooden structure, typical of the Forest Service towers built across Appalachian and National Forest land in the first half of the 20th century. They are designed for height, not shelter. The point is visibility, the ability to see across the canopy and spot the smoke of a fire before it spreads. This means the observer inside is by the tower's very purpose elevated. The walls are thin. The structure is open at the observation level, or nearly so. During the storm that arrived on that afternoon in 1942, rain would have come against the wooden walls at an angle, and the sound inside would have been a kind of enclosure of sound. Rain on wood, wind across the open gallery, thunder arriving in sequence from wherever the storm was centered. And then the bolt came through the structure, traveled the length of Sullivan's leg, and left through his toe, and a clean hole remained in the leather of his shoe. He kept that shoe, or at least accounts of his life suggest he was aware of its significance, that a shoe with a hole burned clean through it by lightning is a specific and documentary artifact, the kind of physical evidence that makes a past event concrete and verifiable in a way that memory alone cannot. The toenail that the strike took never entirely returned to its original form. The body documents what happens to it and carries the evidence forward. The truck incident in 1969 unfolded along a mountain road of the kind that winds through the park in long curves, following the terrain rather than cutting through it. dropping into hollows and rising along ridges and offering, at certain turns, long views out across the valleys to the east and west. Sullivan had been patrolling. The storm was either already present or arrived quickly. Mountain weather in August in the Appalachians can develop faster than a driver on a narrow road can reasonably respond to it. The bolt came from a nearby tree. The deflection of lightning from one object to a second is a documented and not uncommon phenomenon. The bolt finds its initial point of contact, and the energy can jump from there to a person or object in close proximity. The eyebrows are the detail that stays, their complete absence after the event, and the fact that Sullivan had to be told or had to discover this in a mirror at some point after regaining consciousness is a small and specific fact among larger ones, and it is the specificity of it that makes the event feel real rather than reported. The Park Service documentation of Sullivan's strikes would have followed the standard procedure for workplace incidents: a written account of what occurred, when, where, the nature of the injury, any medical treatment that followed, witnesses where present, filed and kept, duplicate copies sent to the relevant administrative office. The incidents accumulating in a file that grew over the years into something unlike any other personnel file in the service's history. When the Guinness verification came, that file and its counterparts, the medical records from the hospitals that treated him after various strikes, the contemporaneous accounts from colleagues and bystanders, made it possible to do what verification requires, and why to trace each event backward to its documentary moment, to confirm that what was claimed had been recorded in real time by people who had no reason to inflate or distort it. 7 documented strikes, the 7th and final, of which Sullivan survived. The thing he had carried through his career, the accumulation of it, the strange and growing arithmetic of strikes, had become by his later years a kind of identity. Local and national press had written about him. The Guinness recognition had given his situation a public form. He had a nickname, the human lightning rod, which was the kind of informal label that attaches to a person when what has happened to them becomes more than most people know how to hold. He gave interviews. He answered questions. He described his experience of the strikes and the growing conviction that something was seeking him, and these descriptions were noted down and published, which is how they have survived and become part of the record. What Sullivan reported was not rage or bitterness toward the sky. He described fear, a fear that had grown with the strikes and that had changed the way he moved through the landscape he had spent his career working. He described the precautions he had come to take, the can of water on the seat of his truck, the vigilance about cloud formation, the particular attention to weather systems building over the ridges. He described a loneliness in it, a sense of isolation that came from carrying something that no one else had experienced in the same way, and that most people encountered, when they encountered it at all, as a curiosity rather than a life. These are reported recollections and interview accounts, not a private record or a journal, and they carry the usual limitations of anything that has been translated into the third person and printed. But the pattern of what he described, across multiple interviews given to different journalists over different years, is consistent enough that it holds a shape. The can of water is the detail that holds a particular kind of weight, not a bottle, not a fire extinguisher or a large container. A can, the kind of modest, practical object a person keeps within arm's reach when they have decided that preparedness is the only available response to something that has already proven itself willing to find them. He set it on the passenger seat. Every morning, before beginning the route, he started the truck and he drove the mountain roads of Shenandoah National Park and the can rode beside him, dented from use, its water shifting slightly with the curves of the road, and he watched the sky the way that only someone who has earned a particular education in it learns to watch. The Blue Ridge in any season is a landscape that asks to be seen. The long views from the higher ridgelines extend in both directions across the spine of the mountains, and on clear days the light moves across the western slopes in a way that arrives and changes and settles with the hours. On mornings without weather, the ridgeline carries the specific quiet of a high forested place before the day has fully begun. Bird call inside the trees, a stillness on the exposed sections, the sky a pale and open thing above the canopy. In all those mornings, across all those years, Roy Sullivan walked and drove through that landscape, and the landscape was his work and his knowledge and the terrain of the longest part of his life. Shenandoah gets its name from a word in the language of the people who lived in and around these mountains, long before the Park Service existed and long before lookout towers rose above the trees. The name is rendered variously in different sources, and its precise original meaning is debated, but many accounts translate it as something like Daughter of the Stars, a phrase that connects the mountain landscape to the sky above it in a way that has nothing to do with lightning and everything to do with the relationship between high land and open heavens that anyone who has spent time on these ridgelines can recognize from the inside. Sullivan would not have needed the translation. He knew the mountains, and he knew what the sky did from them, and he knew it in a way that had become particular to him and to no one else. 36 years is a long career in any line of work. In outdoor terrain work, in mountain weather, it is a long time to be exposed to what the sky does. The Appalachian weather systems that move through Shenandoah in summer carry the specific intensity of humid eastern mountain weather, warm, wet air rising against the ridge, cooling and condensing, building the storm structures that characterize these mountains in July and August. A person working outside in this terrain across 3.5 decades becomes familiar with the signs, the particular quality of the light before the cumulus begins building, the drop in temperature, the shift in wind direction, the first sound. Sullivan would have known all of these, and knowing them, and watching for them, and carrying the can of water, he drove the morning routes through the park and did his work, and came home in the evenings and went out again the next day. The Guinness listing placed his experience inside the category of the documented and verifiable. Whatever the statistics say should be possible, and whatever probability suggests about the likelihood of 7 strikes to a single person in one lifetime, the records say it happened, and the records were made by people with no reason to fabricate them. The verification team's work, turning through the pages of incident reports and medical files in a quiet office somewhere, assembling the documented proof of something that the numbers insist should not exist, produced an official record that sits in the archive with every other Guinness record, beside the tallest buildings and the fastest swimmers and the longest fingernails, which is perhaps the most ordinary and the most extraordinary thing about it. What Sullivan made of the recognition and what it changed or did not change about his daily life in the park is not fully recorded. He kept working for years after the later strikes. He kept the can of water on the seat. He gave the interviews when asked and described what had happened to him and what it felt like, with the careful precision of someone who knows that the facts of their own experience are the only authority they have on the subject. He was not a researcher or a physicist or a meteorologist. He was a man who had worked a particular stretch of Blue Ridge terrain for most of his adult life, and who had been struck by lightning 7 times, and had survived all 7, and had kept going out the next morning, and the morning after that. In the long context of a working life, the strikes and the years between them exist together, the ordinary patrols and the logged incidents, the clear days and the storm days, the mountains continuing their work of being mountains, and the sky continuing its work of being the sky. The file in the Guinness archive holds 7 reports. The can of water held whatever water Sullivan put in it each morning. The Blue Ridge holds the same long shape it has held through seasons and storms and the lifetimes of everyone who has ever walked its trails. And on the passenger seat of a Park Service truck, on some morning in the middle of his career or the later part of it, a dented tin can rides along through the curves of a mountain road, its water shifting quietly with the movement, carrying with it the full quiet weight of a precaution taken by a man who had learned, from experience no one else shared, what it meant to prepare for something that had already found him 6 times, and for whom a 7th morning was simply the next morning, and the can was what he brought to it. The exact appearance of the can is not recorded anywhere in the surviving accounts. Whether it was a coffee can or a paint can, or something that had originally held something else entirely, is not a detail that any of the journalists or researchers thought to ask, or at least not one that made it into what was printed. It is a small gap in the record, the kind that the archive leaves in ordinary things while preserving the extraordinary ones. What is recorded is that he carried it, that he set it on the seat beside him, that it was by his own account part of how he went about his days in the Blue Ridge, and part of what the morning looked like when Roy Sullivan, ranger and survivor of 7 documented lightning strikes, pulled the truck door closed and started the engine and drove out into the mountains that had claimed him and never finally kept him. A cumulonimbus cloud builds slowly over an Appalachian ridgeline on a summer afternoon, its base flat and dark against the tree line, its upper body piling upward in great rounded towers of white that compress and spread as they reach the highest, coldest air, flattening into the wide horizontal shape that meteorologists call an anvil. The process has been underway for hours. What began as a low, innocent heap of fair weather cloud over the warmer air of the valley floor has climbed without apparent effort through 10 kilometers of atmosphere, drawing up heat and moisture in long invisible columns, organizing itself with the patient thoroughness of something that has been doing this for 4 billion years. The anvil top is now spreading downwind. Inside, something has been accumulating. The interior of a mature thundercloud is in constant motion in every direction at once. Powerful updrafts pull warm, moist air upward at speeds that can exceed 150 kilometers per hour, while downdrafts drive colder air back toward the ground along separate channels, so that within a single cloud system, air is rising and falling simultaneously in adjacent columns, passing through each other, colliding, mixing, and separating again in patterns too complex for any single observer on the ground to fully picture. What rides inside those currents matters enormously. At the lower, warmer levels of the cloud, water droplets form and accumulate. Higher up, where temperatures fall well below freezing, those droplets become ice crystals, thin hexagonal plates and columns of frozen water, lightweight and easily carried. Higher still, in the deep cold near the cloud's top, larger particles form, clumped, soft clusters of frozen droplets, called graupel, heavier than the crystals above them, dense enough to fall back toward the cloud's center under their own modest weight. Between the rising ice crystals and the falling graupel, something passes. Contact is the word, though it barely captures what happens. The lighter ice crystals and the heavier grapple collide constantly, billions of times per second, throughout the cloud's interior, and each collision, through a process that researchers continue to study with considerable care, transfers a tiny quantity of electrical charge from one particle to the other. The process is called non-inductive charging, meaning it does not require any external electrical field to drive it. The charge separates simply through the act of particles colliding and parting. The lighter ice crystals, after each contact, carry a small positive charge. The heavier grapple, after the same contact, carries a small negative charge. Lifted by updrafts, the lighter crystals travel upward. Pulled down by gravity, the grapple settles toward the base of the cloud. Over the course of an hour, then 2, then 3, the cloud sorts itself. Positive charge accumulates near the top, negative charge pools near the bottom. What began as a heap of undifferentiated cloud has become an enormous battery, and the potential difference between its poles, the gap in electrical pressure between the negative base of the cloud and the positive surface of the Earth far below, can reach hundreds of millions of volts. At that scale, the air itself begins to be insufficient insulation. Air is ordinarily an excellent electrical insulator. Its molecules are spread too far apart to easily conduct a charge. But at potential differences of this magnitude, the pressure building between the cloud's base and the Earth begins to ionize the air along narrow branching paths to strip electrons from their parent atoms and create channels of conductive plasma, thin as a finger, where current can flow. This is where the process becomes something the eye might eventually see, though for a long while, everything that happens takes place in total invisibility. A channel begins to form downward from the cloud's base. It does not descend continuously or smoothly, the way water runs down a slope. Instead, it moves in discrete steps, short bursts of ionization, each approximately 50 meters long, each lasting only a few tens of microseconds before it pauses. The channel extends downward, pauses, extends again, branches, pauses again. The branching looks to a physicist who can observe it in slowed time, remarkably like a root system growing downward through soil, not a single straight line, but a forking, exploratory network feeling its way through the path of least resistance in the air below. Each extension happens at a speed of roughly 200,000 meters per second, which sounds very fast and is, in everyday terms, but is measured in the context of what comes later as something almost leisurely. This descending ionized structure, invisible to the naked eye, extending in pulses, branching as it goes, is called a stepped leader, and it carries with it the accumulated negative charge of the cloud base, pressing downward toward the waiting positive Earth. The stepped leader has been propagating for perhaps 20 milliseconds. On the ground far below, something begins to happen in response. Positively charged particles in the soil and in the surfaces of objects on the ground, trees, grass, fences, the metal frame of a power line, the shallow dome of a person's head and shoulders, begin to migrate upward. In tall, exposed, or conductive objects, this positive charge rises toward the topmost point and begins to reach upward into the air, forming its own narrow channel of ionized plasma called a streamer. The streamer cannot be seen either. It rises perhaps a few meters, perhaps a few tens of meters in extreme cases, from the tip of a tree or antenna or other elevated object, feeling upward through the air in the direction of the descending leader, and it waits. The gap between them narrows, step by step, pulse by pulse, as the leader approaches from above and the streamer reaches up from below. In the last few hundred meters, the speed of closure becomes almost instantaneous. When the stepped leader and the ground streamer connect, and from any particular object on the ground, the connection is made with a specific one of the leader's many branches, not with the leader as a whole. A continuous conductive path is established between cloud and earth. This moment of connection, this invisible meeting of descending negative and rising positive plasma channels in the air above a field, or a ridgeline, or a rooftop, is not itself the lightning. What happens in the instant after is the lightning. The conductive path is now complete, and the enormous charge difference between cloud and ground has a channel through which to equalize. The current does not travel downward, it travels upward, surging from the ground through the completed path into the cloud above in what is called the return stroke, a pulse of current so massive and so fast that the air surrounding the channel is heated in a fraction of a millisecond to temperatures of roughly 30,000 Kelvin. 30,000 Kelvin. The surface of the sun, by comparison, sits at approximately 5,500 Kelvin. What surrounds the lightning channel for the duration of the return stroke is a column of plasma roughly twice as wide as a human thumb, briefly 5 times hotter than the sun's visible surface, and the response of the air to that sudden and extreme heating is immediate. The heated air expands explosively outward in all directions from the channel, faster than the speed of sound, producing a wave of compressed air that propagates outward and eventually reaches the ears of anyone within range as a crack, a rumble, or both, the sounds varying with distance and with whether the observer is hearing the nearest point of the bolt or the farther, curved sections that arrive slightly later. Thunder is the record of the channel's shape, written in sound. A long branching return stroke produces a long rolling rumble because different parts of the bolt are different distances from the ear, and the sound from each section arrives in sequence. The whole sequence, stepped leader, descending, streamers rising, connection made, return stroke surging upward, takes less than half a second. In many strikes, the process repeats. A second and third, and sometimes fourth, return stroke will follow the first, along the same ionized channel, each triggered by a new leader called a dart leader that travels the pre-ionized path much more quickly than the original stepped leader, and each producing its own return stroke up the same channel. This is why lightning often appears to flicker. The human eye, sensitive to the momentary dimming between return strokes, perceives the separate pulses as a rapid repetition rather than a single continuous flash. A strike that appears to flicker 3 times has delivered 3 separate return strokes along a single channel, each carrying its own surge of current into the cloud above. Not all lightning reaches the ground. The vast majority of lightning, roughly 3 out of every 4 discharges in a mature thunderstorm, never leaves the cloud system at all. These are intra-cloud discharges, occurring between differently charged regions within the same cloud or between adjacent clouds, and they produce the flickering, diffuse illumination inside a storm system that sometimes lights up an entire cloud bank from within. What observers on the ground sometimes call sheet lightning, a strike that reaches the ground, cloud-to-ground lightning, represents only about a quarter of all electrical discharge activity in a storm, and the conditions that make ground contact more likely include the height of the cloud base, the steepness of the electrical potential difference at the cloud's lower edge, and the presence and height of objects on the ground beneath. Ground-to-cloud lightning also occurs, though much less commonly, from very tall structures, communications towers, skyscrapers, high mountain peaks. Upward leaders can initiate independently, reaching up into the electrical field of an overhead storm and triggering their own return strokes. These upward initiated strikes are common enough at certain structures that engineers account for them specifically in lightning protection design, and they are the reason some very tall towers are struck by lightning, not occasionally, but many dozens of times per year. The overall rate of lightning activity across the Earth's surface is, if held at a certain distance, almost rhythmic. At any given second, roughly 40 to 50 cloud-to-ground lightning bolts are striking somewhere on Earth. Over the course of a year, the total count reaches into the billions, but the distribution of all that activity is not uniform. Central Africa, particularly the region around the Congo Basin, sees the highest lightning flash densities on Earth, a product of the intense solar heating of a continent straddling the equator, combined with the availability of abundant moisture. In Venezuela, the mouth of the Catatumbo River, where it empties into Lake Maracaibo, generates a storm system so persistent and predictable that it has burned continuously on most nights for centuries, producing lightning at a rate sometimes exceeding 20,000 individual bolts in a single evening, a phenomenon so reliable that sailors once used it to navigate the Caribbean. A map of global lightning density, seen from above, would show these hotspots glowing against a background of activity spread unevenly across tropical landmasses, with the oceans and polar regions comparatively dim. The specific geography of a storm's electrical activity also follows patterns that observation and instrumentation have made legible, though not entirely predictable. Terrain affects storm development strongly. Ridgelines and mountaintops force rising air into taller, more vigorous convective cells. The Appalachian Mountains, running in their long southwest to northeast corridor up the eastern United States, generate summer thunderstorm activity with notable frequency, partly because the modest elevations of their ridgelines and the broad, moist valleys between them provide exactly the combination of forced lifting and moisture supply that helps storms develop and sustain themselves through a summer afternoon. The storms that formed over the Blue Ridge in the mid-20th century were not unusual storms by Appalachian standards. The storms were doing what storms do in that place, and at that time of year, following the same atmospheric logic that had governed their predecessors for millennia. A lightning bolt entering wet sand on a beach or in a sandy riverbank does something that is easier to hold in the mind than the abstract facts of return strokes and plasma channels. The current travels down through the grains, superheating them in the fraction of a second the discharge lasts, fusing the silica into glass along the path the bolt has taken through the substrate. What remains, if the surrounding material is carefully removed, is a slender, irregular tube of glass, smooth on its inner wall, where the lightning passed, rough and irregular on its outer surface, where the fusion tapered off, branching where the current branched, curling and bending with the variations in the sand's conductivity. These are fulgurites, and the longest recorded specimens have been recovered from depths of 5 meters or more, preserving in glass the complete three-dimensional shape of the bolt's path through the earth, with a fidelity that no photograph of the lightning itself could achieve. The lightning is gone in microseconds. The fulgurite, if left undisturbed, will remain for geological time. Some of the grains of quartz fused into a fulgurite were already hundreds of millions of years old when the bolt arrived. The glass that joins them will outlast the sand around it many times over. A specimen recovered carefully from a beach, brushed clean and held up to light, shows the branching. The main tube, perhaps the width of a finger, sends off narrower subsidiary branches at irregular intervals, each of those branches narrowing further and terminating in a fine point. The shape is entirely consistent with the shape of the stepped leader that created it, the primary channel and its subsidiary branches preserved in exact proportion, frozen in the moment the return stroke superheated the sand around them. The outer surface of the glass is rough and pitted with embedded sand grains. The inner surface is smooth, glassy, and often iridescent in certain light, the way the inside of an oyster shell is iridescent, the product of rapid, intense heat applied for a very brief time to material that was not expecting to become glass that afternoon. The chemistry of fulgurite formation varies with the composition of the sand. Quartz-rich sands produce a clear or pale gray glass. Sands with higher iron content produce darker, sometimes greenish tubes. In soils with significant organic material, the products are more complex, less regular, and less well preserved. The conditions most likely to produce a clean, recoverable fulgurite are dry, loose, silica-rich sand and a direct high-energy strike, which is to say, a beach or a sand dune on a day when the storm delivers a particularly vigorous discharge. These conditions align often enough that fulgurites are not extraordinarily rare. A person willing to probe sandy soil around the apparent point of impact after a beach storm will sometimes find one within a foot or two of the surface. Most are small. The impressive ones, long, branching, structurally intact, require careful excavation and considerable patience, but they exist in museum collections around the world, each one the cast of something that happened too fast to see. The return stroke's heat is not only destructive in the immediate sense. Along with fusing sand and heating air, it produces ultraviolet light, X-rays, and gamma radiation, the last of these only recently documented by researchers using gamma-ray detectors placed near known lightning activity. The discovery that lightning produces gamma radiation in brief pulses corresponding exactly to return strokes revised an assumption that had been broadly held, that the temperatures and energetics involved, high as they are, were not sufficient to produce ionizing radiation in detectable quantities. The gamma pulses are weak by the standards of other radiation sources and dissipate rapidly, posing no practical concern for anyone in the vicinity of a storm. What they indicate is that the physics of a return stroke is somewhat more energetic and complex than the models used before their detection had assumed, and that the study of lightning, a phenomenon so common that a city might experience hundreds of strikes in a single summer, continues to produce measurements that revise even well-established figures. The color of lightning, seen directly, varies. The most common color is white or pale blue-white. The composite emission of the superheated air column, which radiates across much of the visible spectrum simultaneously, with some wavelengths dominant, depending on altitude, humidity, and air composition. Lightning observed through rain often appears more yellow or orange, the shorter blue wavelengths scattered by water droplets before they reach the eye, leaving the longer red and orange wavelengths proportionally stronger. Very high altitude lightning, at the tops of thunderstorm systems, sometimes appears distinctly blue. Lightning in dust storms or smoke can appear orange-red throughout. The variations are the same kind that produce the colors of sunsets, selective scattering by particles in the air between the source and the observer, and the underlying white of the channel itself is always the same broad, hot emission, regardless of how it arrives. Above thunderstorms, the atmosphere produces electrical phenomena that took decades of credible observation and eventual instrumentation to document properly. Red sprites are brief, large-scale electrical discharges that propagate upward from the tops of active thunderstorm cells into the mesosphere, 50 to 90 kilometers above the Earth's surface, lasting only a few milliseconds each, and appearing as diffuse columns or jellyfish-shaped structures of reddish light, sometimes extending upward 20 to 30 kilometers. They were reported by pilots for many decades before they were captured on camera in 1989 and formally recognized. Blue jets propagate upward from storm tops in narrow cones of blue light, reaching into the stratosphere. Elves, a name that began as an acronym and became simply the name used in practice, are ring-shaped halos of light that expand horizontally outward in the ionosphere at roughly 90 kilometers altitude. Each one the electromagnetic response of the ionosphere to the intense pulse of a large return stroke below. These phenomena are not hypothetical elaborations. They occur millions of times per year. They were simply happening above every thunderstorm that anyone had ever watched from the ground, invisible from below, until the right instruments and the right vantage points were brought to bear on them. A storm seen from a high-altitude research aircraft above cloud level is a different thing entirely from a storm seen from the ground. The aircraft sits above the anvil top of the cloud, looking down at a system that from below appeared dark and turbulent and tall. From above, the anvil is white and flat, spreading across the sky like a table. Below its surface, the lightning is happening, red sprites reaching up toward the aircraft's altitude, the cloud flickering from within, the bases of the cloud dropping rain into the valley below. The storm is the same storm. The view determines almost everything about what is available to perception. The rate at which a storm produces lightning varies considerably. A modest summer thunderstorm over an inland area might produce only a few cloud-to-ground strikes over its lifetime. A large, organized supercell thunderstorm can produce strikes at rates exceeding 10 per minute for hours at a time, with its electrical activity waxing and waning as it cycles through stages of convective development. The storm over Lake Maracaibo does not produce 20,000 strikes per evening, because any single storm cell is unusually intense. It produces that count because the same meteorological conditions that generate storm development there operate predictably night after night. With new cells forming and old ones decaying in a nearly continuous cycle driven by the lake's geography, the surrounding mountains, and the convergence of specific wind patterns that have not changed in any meaningful way since the sailors first noted the light on the horizon. The lake system itself has been proposed as an aid to navigation, so reliable that it appeared on 17th century maps with annotations noting the perpetual storm. The lightning visible from the Catatumbo at distances of up to 400 kilometers was used by sailors to orient themselves on the Caribbean, not because the storm told them where they were with any precision, but because the glow on the horizon in a specific direction was a reference point they could return to whenever the night was clear enough to see it. A lighthouse built from weather. It continues to operate, a slender glass tube curled through former sand, recovered from a damp beach and held gently in one hand, branches in two directions about 2/3 of the way down its length, before both branches taper to points thin as a pencil line. The main body is rough on the outside, where the grains adhered as they fused, smooth on the inside where the lightning passed. Its weight is almost nothing. Held to light, the inner surface catches and scatters the light in the way of old glass, not the clean transparency of modern manufacture, but the slightly uneven, slightly iridescent surface of something made very fast, under very strange conditions, and never polished afterward. The bolt that made it cross the full gap between a cloud and the earth below in a fraction of a second. What it left in the sand has been cooling ever since, and will cool for a very long time to come, a record written in glass of a path that existed for barely an instant and will outlast nearly everything that was alive. The afternoon the storm passed through. Ground current spreads outward from a lightning strike point in widening rings, moving through wet soil the way water moves through cloth, radially, invisibly, following the path of least resistance in every direction at once. It reaches through the earth without surface, without sound, without any visible sign of its passage. A person standing 50 feet from where a bolt has entered the ground might feel nothing at all. A person standing 10 feet closer might not survive the next few seconds. The difference between those two outcomes is not the storm, it is geometry and moisture and the exact distance between one person's feet. This is where the body's encounter with lightning most often begins, not from above, not from a direct strike out of the sky, but from below, from the ground itself, from a charge that has already done its primary work and is dispersing outward through everything it can reach. Ground current is responsible for more lightning fatalities across the world than any other mechanism. It enters through one foot and exits through the other, traveling up through the legs and across whatever internal territory lies between them. The path it takes depends on what it finds. And what it finds in a living body is a great deal worth conducting. There are 5 distinct ways lightning can enter a human body, and each one leaves a slightly different mark. A direct strike is the most obvious, the bolt choosing a person as its final terminal, which happens less often than most people assume, in part because a standing human being is rarely the tallest object in the available landscape. A side flash occurs when a bolt strikes a nearby object, and a portion of its energy jumps sideways through the air to a person standing close to it. The way current will cross a gap if the gap is small enough and the charge large enough. Contact injury happens when a person is holding or touching something the bolt has struck directly, a fence post, a golf club, a telephone handset, in an older era. Upward streamers, the rising channels of positive charge that reach toward a descending leader from the ground and from objects on it, occasionally discharge through a person's body, even when the main return stroke connects with something else entirely, leaving an injury without the full force of a direct strike. Each mechanism produces a different pattern of entry and exit. Each produces a different distribution of current through the tissues it crosses, and yet across all 5 mechanisms, one feature of lightning injury distinguishes it most sharply from other forms of electrical trauma, and that feature is not the voltage or the temperature of the arc or the force of the associated pressure wave. Though all of those are remarkable in their own right, the distinguishing feature is how briefly the current lasts. A person who contacts a household electrical circuit receives current that continues to flow for as long as the circuit remains closed, which in an accident may be several seconds or longer. The muscles clamp. The grip tightens rather than releasing. The exposure accumulates. Lightning works entirely differently. The duration of a lightning strike's current passage through a body is measured in milliseconds and often in fractions of a millisecond. The whole event, from first contact to the dissipation of the return stroke, takes less time than the blink of an eye that the body has not yet had time to register has happened. The charge that moves through or across a person in that interval is enormous. The interval itself is extraordinarily short. This brevity is the reason a phenomenon called flashover is so significant in lightning survival. When current arrives at the body's surface with enough speed and enough charge, and when the surface is damp, as a person caught outdoors in a storm very often is, the current tends to travel along the outside of the body rather than plunging through the interior. It finds the surface faster. Water conducts well. Skin, when wet, offers a route that diverts the charge away from the organs and vessels and muscle beneath. The current moves across the person the way a river in spate moves across flat ground, finding the exterior contours, sweeping across them, and discharging into the earth through the feet or the hands, having traversed the surface rather than the depths. Flashover does not prevent injury. The pressure wave associated with a nearby strike is enough on its own to throw a person off their feet. The current, even traveling on the surface, disrupts function. Burns occur at the entry and exit points and along any portion of the skin through which significant current passed. But flashover does mean that the internal architecture of the body, the heart, the lungs, the kidneys, the long tracts of the central nervous system, is partly shielded from the full force of the discharge by the simple fact that the wet skin offered a faster way through. It is a protection that is partial, variable, and not something a person can plan for or rely on. Whether it occurs depends on how damp the surface is, on how exactly the strike arrives, on geometry that no one could calculate in advance. But in the documented record of lightning strike survivors, flashover appears again and again as the mechanism that made survival possible, where the raw force of the charge should, by other measures, have made it unlikely. The heart, when lightning current reaches it, undergoes something that the rest of the encounter has not prepared for. The entire muscle depolarizes at once. Under ordinary circumstances, the heart's electrical system fires in an organized sequence, a wave of activation that begins at the sinoatrial node in the right atrium and travels through the tissue in a carefully timed cascade, contracting the chambers in the right order and then resetting for the next beat. Lightning current does not follow that sequence. It does not begin at the sinoatrial node and proceed in an orderly direction. It arrives everywhere simultaneously, depolarizing every cell in the muscle at the same instant, leaving the whole system in the same state, discharged, reset, waiting. What happens next depends on how the cells recover. Ventricular fibrillation, the arrhythmia in which the ventricles contract rapidly and chaotically without pumping blood, is the leading cause of death in lightning strike victims. The current disrupts the orderly sequence, and the system restarts, not in rhythm but in a quiver. Without restoration of normal rhythm, perfusion fails. But the heart intrinsic pacemaker cells, once the disrupting charge has dissipated, may simply resume on their own. The sinoatrial node fires. The cascade reestablishes itself. The heart, finding itself in the same recovered state it returns to after any depolarization event, does what it was built to do. It starts again. This spontaneous recovery is documented in lightning strike victims who were found pulseless, in whom no external resuscitation was performed, and who survived. It is not reliable. It does not occur in every case, but it occurs, and it occurs specifically because the duration of the insult was so brief that the disruption, once removed, left the intrinsic pacemaker free to recover and restart. The heart that has been fibrillated by a prolonged electrical contact has less opportunity for this. The heart struck by lightning may in some circumstances behave more like a system interrupted than a system destroyed. In the hours after a lightning strike, while the survivor is in a hospital or resting wherever the strike found them, something begins to appear on the skin. It starts as a faint redness, easy to overlook in the general assessment of a person who may have burns, may be disoriented, may be in pain from the pressure wave that threw them. By the time the initial examination is complete, it may already be more visible. By the following morning, it is typically clear. The pattern is branching. It extends outward from a point or a line, following paths that divide and subdivide the way river deltas divide, the way frost forms on cold glass. the way roots spread through soil in search of water. It is reddish brown, slightly raised, warm to the touch in its earliest hours. It traces the exact path that current took along the skin's surface, the capillaries ruptured by the passing charge, mapping themselves out in a branching diagram of where the flashover traveled. The pattern is called a Lichtenberg figure, named for the 18th century German physicist who first described the branching formations produced by static electrical discharge. On a human body, a Lichtenberg figure typically spans a large area, across a shoulder, down a back, spreading from a point of entry across the chest or up from the legs. The branching is not random in the way that ordinary bruising is random. It follows principles. It subdivides at regular angles. It reaches persistently and specifically along the paths of least resistance that the skin's surface offered in the fractional second the current was in motion. Looking at a Lichtenberg figure in a clinical photograph is something like looking at a map drawn by the lightning itself, a record of exactly where it went, rendered in the body's own red response to the passage. A Lichtenberg figure is pathognomonic for lightning injury. In clinical medicine, pathognomonic means that the finding alone is sufficient to confirm the diagnosis, that it does not occur from other causes, that when a physician sees it, the question of what produced it is answered. A Lichtenberg figure on a person who was found outdoors after a storm, unconscious and unresponsive, ends the diagnostic uncertainty about what happened to them. It does not appear in high-voltage electrical injury from power lines or household circuits. It does not appear in burns from other sources. It appears only where a surface flashover has mapped the capillaries in the seconds after a lightning discharge. Within 24 to 48 hours, the figures begin to fade. The capillaries that ruptured during the flashover do not leave permanent damage in the surrounding tissue. The extravasated blood is gradually reabsorbed. The red branching lines become lighter, then pink, then the faintest suggestion of a pattern, and then nothing. The skin returns to its ordinary surface. A person examined 3 days after a lightning strike may show no external trace of the Lichtenberg figures at all, even if those figures on the morning after the strike covered a substantial portion of their torso or back. This impermanence means that if the figures are not observed and documented while they are present, the confirmation they offer disappears with them. In emergency settings, where a lightning strike victim may have been brought in unconscious and assessed rapidly for life-threatening injuries, the Lichtenberg figures can be missed entirely, observed by no one, fading over the following days, leaving the person without the one finding that would have confirmed, beyond any question, what had happened to them. In some documented cases, the origin of a victim's neurological or cardiac symptoms was initially unexplained until the history was reconstructed and the possibility of an unwitnessed lightning strike was raised. The neurological system, reached by lightning current both directly and through the pressure wave of the associated blast, undergoes disruption that extends far beyond the immediate event. The immediate effects are varied and often dramatic: loss of consciousness, which is common, chronoparalysis, a temporary paralysis, and loss of sensation in the limbs that can appear severe enough to suggest permanent spinal injury and that resolves on its own over hours, confusion, amnesia for the event and for some period around it, and what survivors frequently describe, not as the pain of electrical shock, but as a sudden, total impact, as though the body was struck by something large and fast from every direction at once. Coronoparalysis is worth dwelling on briefly because it is something that has led to significant diagnostic confusion in emergency settings. A person brought in from a lightning strike scene with cold, pulseless, apparently paralyzed limbs presents a picture that might suggest severe vascular injury or spinal cord damage, or both. The skin may be mottled and discolored. The pulses at the wrists and feet may be absent or very faint. Under ordinary circumstances, that combination of findings would prompt urgent vascular surgery consultation or would begin the evaluation for spinal cord injury with very limited expectations of recovery. In lightning strike victims, this presentation is typically a vascular spasm, a temporary, reversible constriction of the peripheral vessels in response to the current that passed through or near the vascular system. The limbs are cold because blood is not reaching them freely, not because the vessels have been permanently damaged. The pulses are absent or diminished because the vessels are constricted, not because they have been torn or blocked. Within hours, as the spasm resolves, circulation returns. The limbs warm, the pulses reappear. A person who appeared, on arrival, to have sustained massive vascular or neurological damage to all four extremities is by the following morning moving those limbs freely. The importance of recognizing coronoparalysis is that treating it as permanent injury or performing surgical interventions appropriate to vascular trauma would be both unnecessary and potentially harmful. It resolves. It needs time, not intervention. And a clinician who has not encountered lightning injury before, or who encounters it rarely, may not have the pattern recognition to hold back and wait through what looks like a deteriorating clinical picture. The acute disruption of lightning injury, the cardiac arrest that may resolve on its own, the coronoparalysis that fades overnight, the Lichtenberg figures that appear in the morning and are gone by the following week, has a counterpart that is less dramatic and considerably more persistent. The neurological sequelae of lightning injury extend in many survivors over months and years, producing a pattern of symptoms that researchers who have studied lightning strike survivors over time have come to recognize as a consistent and under-recognized syndrome. Chronic pain is reported by a substantial proportion of long-term survivors. It is often neuropathic in character, burning, aching, or shooting pain that does not correspond to any specific injury site and that fluctuates over time without a clear relationship to activity or rest. Sleep disorders are common. The disruption to the autonomic nervous system, which regulates the transitions between waking and sleep, among many other functions, can produce difficulty falling asleep, difficulty staying asleep, and a quality of rest that does not restore in the way sleep is supposed to restore. Survivors who report good physical recovery from their acute injuries may still describe, years later, a fatigue that sits beneath the surface of their ordinary days. Cognitive changes occur across a range of domains. Attention and concentration are affected most commonly. The ability to hold a sustained focus on a task, to follow a train of thought without interruption, to retrieve a word or a name that should be immediately available. The experience of this, described by survivors in clinical interviews, is often one of a mind that is present but slightly delayed, working harder than it should to produce results that used to come without effort. Memory, both for the period immediately around the strike and for new information in the months that follow, may be inconsistent in ways that are frustrating, precisely because the person knows, from their own earlier experience, how their memory previously worked. Personality changes are documented as well, not dramatic transformations, but shifts in baseline irritability, in emotional regulation, in the degree of patience available for noise or activity or demand. The neurological disruption of the strike does not localize neatly to one region of the brain. The current's passage, the pressure wave, the associated hypoxia during any period of cardiac arrest, All of these affect neural tissue in ways that distribute across the system rather than concentrating in one place. The behavioral and emotional effects that follow are similarly distributed, difficult to attribute to a single mechanism, and easy to misinterpret from outside as personality traits rather than the consequences of a specific physical event. One of the stranger and more consistently reported features across lightning strike survivor accounts is a heightened sensitivity to sensory input. Light may become more difficult to tolerate than it was before. Loud environments, a restaurant, a busy street, a room where several conversations are happening at once, may produce a level of distress out of proportion to what the same environment would have produced in the same person before the strike. The hum of electrical equipment, which most people filter out entirely without noticing, may register at a level that is difficult to ignore. The sensory threshold appears to have shifted in a direction that makes the ordinary world louder and brighter and more present than it was. This heightened sensory sensitivity is not simple hypersensitivity in the sense of an allergic or inflammatory response. It appears to reflect a change in the way the nervous system processes and filters input, a change in the gain of the system, so that signals that previously would have been suppressed or normalized before reaching conscious attention now arrive more directly and with more weight. The nervous system, after the disruption of a lightning strike, may have recalibrated in ways that take months or years to settle, and in some survivors may never fully return to their baseline. The University of Florida's Lightning Research Group, which has compiled and analyzed survivor records over decades, describes this constellation of long-term symptoms as the neuropsychological sequelae of lightning injury, a syndrome that is, as their research consistently notes, under-recognized and under-treated. The acute phase of a lightning strike is dramatic enough to command immediate clinical attention. Burns are dressed. Cardiac monitoring is established. Neurological assessment is performed. But survivors who are discharged from the hospital with good vital signs and no immediately threatening findings may not be followed over the months during which the more subtle and persistent effects of the injury develop. They may present later to general practitioners or to specialists with complaints that do not, in isolation, suggest a connection to the lightning strike event, unless the history is taken carefully and unless the clinician already knows to look for this particular pattern. The body caught in a lightning strike is not a simple conductor, passively accepting whatever charge the storm delivers. It is a system, a collection of systems, each with its own electrical properties, its own response to sudden current, its own timeline for recovery and adaptation. The skin offers the possibility of surface routing. The heart offers the possibility of spontaneous restart. The peripheral vessels go into spasm and then release. The brain and nervous system reorganize over time, not always returning to the exact configuration they held before. What the lightning does to a body is not one thing, it is a cascade of responses, each one unfolding on its own schedule, across an interval that begins in milliseconds and may extend across years. Survivors describe the experience of having been struck in ways that are strikingly similar across accounts collected by different researchers in different decades. The absence of warning, no sensation before the strike, no gradual escalation from mild to severe, just the unmediated arrival of an event that was not present the moment before. The confusion in the immediate aftermath, the loss of the narrative thread of the preceding hour, the difficulty accounting for the gap in experience, the slow reconstruction in the days and weeks after of what the medical record shows must have happened, from a position of having no direct memory of the central event. What strikes researchers reviewing these accounts is how consistently survivors describe the strike itself as having less phenomenological content Then the aftermath. The strike is a gap. The aftermath is a long sequence of small recoveries, adjustments, and recognitions, the gradual understanding of what the body is now doing differently, and of what it may take time to return to, and of what it may not return to at all. The burns from a lightning strike, outside of direct attachment to a high resistance entry path, are often less severe than burns from prolonged high voltage contact, again because of the brevity of exposure. Superficial burns at the sites of current concentration, entry and exit points, areas of skin contact with metal objects like belt buckles, watch bands, or necklaces are common and generally heal in the normal course. Hair can be singed or along the pathway of significant current burned away entirely. Eyebrows and eyelashes, presenting fine surface structures to the heat of the arc, may be completely removed. These are acute and visible consequences, and they heal, most of them in the weeks and months that follow. What does not heal as neatly is the disruption to the distributed electrical function of the nervous system, a system that, more than any other in the body, is built around electrical signaling and therefore sits at the most direct interface with the kind of insult a lightning strike delivers. Nerve cells that have been massively depolarized at once across the entire system do not simply resume their previous state. They function, they adapt, they compensate. But the record of the adaptation is carried forward in the long-term pattern of symptoms that researchers have documented and survivors studied over years. And that pattern is specific enough and consistent enough across independent accounts that it describes something real. The recognition that this syndrome exists, that the long-term neurological consequences of lightning injury constitute a distinct and recognizable clinical picture, is itself relatively recent. For much of the period during which lightning strikes have been survived and documented, the survivors' long-term difficulties were either attributed to other causes or explained to the survivors as residual effects that would continue to improve, or not fully believed at the level of institutional medicine, in part because the acute phase of a lightning strike, once survived, leaves the body looking more intact than other forms of severe trauma. A person who has been in a serious car accident may have visible and permanent physical injuries, whose relationship to the accident is never questioned. A person who has survived a lightning strike may leave the hospital with healing burns and improving vital signs, and may spend the following years describing cognitive and sensory and sleep symptoms that have no obvious acute substrate and that do not, from the outside, map neatly to the lightning strike that occurred months or years before. The syndrome is real, the documentation is there, but the gap between what survivors experience in the long term and what clinical medicine recognized as sequelae of lightning injury took time to close. It is closing now. The research is clearer. The clinical frameworks are more developed. Survivors presenting to informed clinicians with the long-term pattern of fatigue, cognitive change, sensory sensitivity, and sleep disorder are more likely to have those symptoms recognized in the context of their history rather than evaluated in isolation as separate and unrelated problems. The picture is more complete than it was. A Lichtenberg figure on a person's skin begins to fade within a day or two of the strike that made it. The branching red lines which trace the surface current so precisely in the hours after the event grow lighter with each passing morning. By the second day, the pattern that covered a shoulder blade or spread across a forearm may already be difficult to read in full. By the third day, the outlines are soft, the edges have lost their definition. By the time a week has passed, the skin is unmarked. The figure that mapped the exact path of the flashover so completely and so briefly has been quietly reabsorbed, dissolved back into the body it decorated, without leaving anything on the surface to show where it was. The skin is smooth, the pattern is gone. Somewhere in the tissue beneath, the nervous system continues its longer work, in its own time, at its own pace, making what adjustments it can. The ranger station on the April afternoon of the third strike was an ordinary wooden building, maps pinned flat against the walls, a window looking out toward the tree line, rain moving in from the west, and the particular gray light that settles over Shenandoah when a storm is still a few minutes from arriving. The smell of it came through the window frame, that cold, damp smell of air that has been traveling down through mountain cloud before it reaches ground. Outside, a transformer mounted on a pole near the building hummed in the wet air. Inside, a ranger sat with the paperwork of a spring afternoon, the kind of afternoon that feels like a dozen other spring afternoons, because in most respects it was, and would remain, entirely ordinary. Roy Sullivan was 59 years old in April of 1972. He had already been struck by lightning twice, once in a fire lookout tower in 1942, and once in his truck on a mountain road in 1969, and had continued working in the park through both of those events and through the 3 decades between them. The Shenandoah ridgelines had been his daily landscape for most of his adult life. He knew the way storms moved through the gaps in the mountains. He knew which trails flooded and which held. He was, by every account available, a man who had made a settled life inside a particular place, and who carried the knowledge of that place with the ease that comes from long familiarity. What arrived through the building's wiring that afternoon was not, strictly speaking, a direct strike. The bolt came down on the transformer outside, a large metal object mounted on a pole in the rain, which was precisely the kind of object that tends to receive such visits, and the current that entered the building traveled through the electrical system rather than through the walls. Inside the ranger station, by the time the current found Roy Sullivan, it had already passed through infrastructure. It had already been redirected. This is a detail that matters, and the reason it matters is that the station was a protected location, the kind of indoor shelter that all basic lightning guidance describes as safe. He was not in an open field. He was not on a ridge. He was inside a building, doing paperwork on an ordinary spring afternoon. The bolt set his hair on fire. This is documented in the incident report that was filed afterward, and that would eventually travel to a records office in London. The specific way that fire interacted with hair, the way it catches at the roots and spreads with a quiet, quick persistence, is the kind of detail that tends to focus a person's attention very efficiently. What Sullivan reportedly did next is worth pausing on because it says something about a man who had already been through this twice before. He had a bucket of water nearby. The ranger station incident report does not dwell on why the bucket was there, and the accounts Sullivan gave in later interviews about whether he had begun keeping water close to hand, specifically because of his previous strikes, are accounts reported by journalists rather than confirmed in his own direct words. What is in the record is the outcome. The fire was extinguished, Sullivan survived, and the incident was documented. The third strike was done. After that, the press found him. The informal name, Human Lightning Rod, appeared in local Virginia papers and then in wider national coverage, the kind of name that attaches to a story and simplifies it, as names like that tend to do. The story, as the press told it, was a story of improbable and continuing luck, which depended on how a person chose to define luck. Sullivan had survived 3 lightning strikes across 30 years of working in a national park. He had been burned, singed, and briefly unconscious, and had returned each time to the same ridgelines and the same patrol routes, because this was his life, and it was a life he had chosen and continued to choose. Whether the name felt accurate to him is not something the record clearly establishes. The fourth strike came in August of the following year, 1973, on a patrol routes Sullivan knew well. The accounts he gave to journalists afterward are the primary source for what he experienced in the minutes before the bolt arrived, and those accounts describe him watching the storm build behind him in his truck's mirrors. A storm that builds in a rearview mirror is a storm that appears to grow while the driver attempts to move away from it, which is a particular and specific kind of watching. Sullivan told interviewers that he had tried to drive away from the storm. He had seen it forming. He had pressed the accelerator. The storm, by his account, had formed faster than he had driven, and it had caught him on the road. The bolt struck a nearby tree and jumped. This is a recognized mechanism, the side flash, in which lightning current leaves the primary strike object and crosses the air gap to a secondary one, and in this instance, the secondary object was Roy Sullivan, sitting in a truck cab on a mountain road, with a storm visible in his mirrors. The current set his hair on fire again. The regrowth from the third strike, which had taken months, burned away in the same way and in the same location, and Sullivan was thrown against the truck interior by the force of the discharge. He described this event in particular as one he had attempted to escape from. He had done everything a person can do on a mountain road. He had seen the storm, he had identified the risk, he had applied the accelerator and moved in the other direction, and it had found him regardless. The truck drifting on a mountain road, the driver unconscious for some seconds against the door, the storm already moving on into the next valley. This was the fourth time this particular sequence of events had occurred and had resolved, improbably, with Roy Sullivan alive. The hair would grow back again. It had grown back before. The burns on his scalp were the same burns documented in previous incident reports filed under the same name at the same national park. The attending physicians who treated Sullivan after his fourth strike were working with a case history that no medical protocol had been designed to address, because no medical protocol had needed to address it before. There was, by this point, a pattern visible in the documentation. Not a pattern of cause. The individual strikes each had their own specific weather circumstances, their own locations and mechanisms, but a pattern of outcome. The same man, the same park, different trails, different vehicle locations, different points in the month and year and decade, but the same convergence each time of storm system and one particular person. The Guinness Book of World Records had not yet made its formal verification at this point in Sullivan's life, but the material for that verification was accumulating entry by entry in the files of the National Park Service and in the medical records of the regional facilities that had treated him. The documentation was patient and thorough in the way that institutional documentation tends to be. Each incident report written in the plain, careful language of a form designed to record facts rather than interpret them. The fifth strike arrived in June of 1976. Sullivan was on foot on a remote section of the park when the storm caught him, a section of trail distant enough from any building or road that the options for shelter were limited to the trees around him and the topography beneath his boots, neither of which offers meaningful protection when a storm system is directly overhead and moving slowly. The mechanism in this case was ground current, in which the electrical discharge enters the soil at the point of the primary strike and radiates outward in a pattern that follows the conductivity of the ground. The current reached Sullivan through his ankle. The burn documented in the medical records from this event is consistent with the typical presentation of ground current injury, localized and specific, as though the current found a single point of entry and concentrated there. A fellow ranger was present on the trail at some distance when the fifth strike occurred. This is significant in a particular and practical sense because it means that the 1976 event was witnessed by a third party who was in a position to provide a contemporaneous account. That witness filed a report. That report described what they observed, the strike, the conditions, Sullivan's injury, in the language of someone writing down what they had seen while the memory was still immediate. The report traveled eventually through the National Park Service filing system. It became part of the documentation. And when the Guinness verification process later assembled its records, the 1976 witness report was among the materials that contributed to the formal recognition of Sullivan's case as verified fact rather than accumulated legend. The remoteness of the trail where the fifth strike occurred is worth holding for a moment. Remote sections of large national parks are by definition places that receive fewer people than the visitor centers and the paved overlooks and the popular trailheads. They are places that park rangers tend to know well and civilians tend not to reach, places where the distance between a person and the nearest assistance is measured in hours of walking rather than minutes of driving. Sullivan walked those sections as a routine part of his work. The trails were his to patrol, which meant he was regularly in precisely the conditions, elevated terrain, open ridgelines, isolated walking, that increase a person's exposure to lightning risk. This is not a rhetorical point about fate. It is a practical observation about occupational geography. The park was large, and the sky above it was the same sky it had always been, full of the same Appalachian weather systems it had always produced. After 5 strikes across 34 years, Sullivan was 63 years old. He had continued working in the park through all of it. The incident reports existed. The medical records existed. The photographs of injuries at various stages of healing existed in various files. The informal name in the press had become familiar enough that journalists sometimes called the Park Service directly when weather events in the region produced news. Sullivan had outlasted the statistical likelihood of his own experience. He had done so without, as far as the record shows, significant change to the fundamental shape of his life. The patrol routes, the mountain roads, the remote trail sections, the truck moving along the ridgelines, through all weather and season. The 6th strike came in June of 1977, a year after the 5th, and this one was different in a specific medical sense. Sullivan was fishing at a pond near Waynesboro, Virginia. He described the conditions that day to hospital staff afterward as only mildly stormy, the kind of overcast, intermittently unsettled afternoon that is common enough in Virginia in June and that most people would not characterize as particularly dangerous. The pond would have been flat, reflecting the gray sky. The rod in his hand would have been the kind of unremarkable equipment a man uses when fishing is a thing he has done many times in the same places. It was an afternoon that looked from the outside like a very ordinary kind of afternoon. The bolt struck him directly across the chest and abdomen. This is the clinical description that appears in the hospital documentation from the event, and it matters because it describes a more direct and central impact than several of the previous strikes, which had found Sullivan through secondary mechanisms: side flash from a nearby tree, current through a building's wiring, ground current through his ankle. A direct strike across the chest and abdomen brings the discharge into close proximity with the cardiac and respiratory systems. The second-degree burns that Sullivan sustained were serious enough that he was hospitalized for several days. His condition on admission was documented as serious. What Sullivan told hospital staff in Waynesboro is part of the record in the way that patient statements tend to be part of clinical records, noted, acknowledged, and placed alongside the physical findings, without the treating physicians being positioned to verify or refute the experience it describes. He said he believed something was specifically targeting him. He said this not as a figure of speech or a dark joke, but as what appeared to be a genuine statement of his developing understanding of his own life. He had survived 6 lightning strikes. He had walked out the other side of each of them, burned and briefly unconscious, and sometimes dramatically singed, but alive and eventually ambulatory, and eventually back in the park. And he had arrived, after 6, at the conviction that what kept finding him was not random. The clinical word for what Sullivan described is not anything exotic. People who have survived repeated traumatic events sometimes develop frameworks for understanding the persistence of those events, and those frameworks often involve some form of agency, something acting, something seeking, something with intention. This is a common and documented feature of how human minds process patterns that exceed statistical expectation. Whether Sullivan's framework was accurate in any literal sense is not a question the hospital staff were equipped to answer, and is not a question the record resolves. What the record contains is the statement, the date, and the medical findings from the 6th strike. The burns healed. Sullivan was discharged. The incident report was filed. What Sullivan carried with him in the months and years after the 6th strike is described in the interviews he gave to journalists during that period. And those interviews describe a man who had not stopped thinking about the sky. He had developed what he called, in various accounts, a persistent awareness of storms, not the ordinary weather attentiveness of a park ranger, whose job requires knowing what the sky is doing, but something more internal and less comfortable than that. He described checking for storm formations, even on days when the forecast gave no reason for concern. He described what interviewers characterized as a watchfulness that had become habitual, a kind of continuous background monitoring that had been installed, apparently, by the accumulation of 6 events across 35 years. This is the context in which Sullivan began carrying a can of water with him on patrol. The can is mentioned in multiple separate accounts from the period. Journalists who rode with him on patrol sections, colleagues who noticed the habit, and it appears consistently enough across sources to be a reliable biographical detail. The specific reasoning Sullivan reportedly offered for the can was practical in an immediate sense. If the lightning set his hair on fire again, he would have water available to extinguish it. This is not irrational. It is, in fact, the logical precautionary response of a person who has had their hair set on fire by lightning on more than one occasion and would prefer to be prepared. The can sat on the passenger seat. It accompanied him on patrol routes through mountain woodland, where storms came in from the west and moved through the ridgelines and dropped rain against the windows of his truck while he drove. The 7th strike was recorded in June of 1977 by some sources, and the year is occasionally listed as the same year as the 6th, though most of the verified documentation places the final strike in 1977 as well, with the 6th and 7th separated by only a matter of months. By this point, the Guinness Book of World Records had begun its verification process, working through the accumulated documentation, the Park Service incident reports, the medical records, the witness statements, to formally establish what the files already contained. The verification process is itself a kind of document, a team sitting in a quiet office, turning pages, reading the same man's name at the top of 7 separate medical reports across 5 decades, reading the dates, reading the mechanisms, reading the injury descriptions, assembling the proof. Sullivan's 7th and final documented strike left him with wrist and chest injuries. The specific details of the seventh event, like those of the others, made their way into the forms and records that the Park Service maintained, and from those records into the Guinness file. Sullivan survived it, as he had survived all 6 before it. He continued working in the park. The can of water continued riding on the passenger seat of his truck. There is something in the plain accumulation of those 7 incident reports that takes a moment to fully register, not because any single one of them is incomprehensible. Each strike, examined individually, has a mechanism and a location and a set of physical findings that fit within the known parameters of lightning injury, but because of the repetition of the name at the top of each page. The forms are standard Park Service forms. The language is the language of incident documentation. The dates span from 1942 to 1977, which is 35 years, which is longer than most careers. The injuries are different in their specifics. This one to the ankle, this one to the hair, this one across the chest and abdomen, and the same in their fundamental nature. Lightning, one man, the same park, a different afternoon. The probability of being struck by lightning once in any given year is estimated at roughly 1 in a million for an average person in the United States. The probability of being struck 7 times across a single lifetime is a number that requires so many decimal places to express that it ceases to function as a number in any practical sense. It becomes more of a statement about the limits of the model. Sullivan's life did not fit the model. The model was built on the behavior of large populations, and Sullivan was not a large population. He was one specific person in one specific park on a very long series of very specific afternoons. What the model cannot account for is the accumulated particular, the way a life lived on exposed ridgelines and mountain roads and remote trail sections across 35 years of Appalachian weather, creates a relationship with the sky that statistics alone were not designed to describe. Sullivan himself, in the interviews from his final working years, did not have a satisfying explanation for what had happened to him. He had the conviction, reported consistently across multiple accounts, that storms had found him deliberately. He had the can of water on the passenger seat. He had the 7 documented incidents and the Guinness recognition that made those incidents permanently official rather than merely personal. He had the informal name from the press, which had followed him for years, and which reduced something complicated and long and quietly strange to a single phrase that was easy to repeat. He had the burns that had healed, the hair that had grown back twice, the eyebrows that had been singed away and returned, the toenail that had not. What he appeared to carry with equal weight in those same interviews was something separate from the lightning. He described, to more than one journalist, a fear that had nothing to do with storms. He described a fear of dying alone, of being unloved, of having accumulated a remarkable and documented life without having the kind of closeness with other people that, by his account, he had wanted and had not found. This is not a claim that can be verified through incident reports or medical records. It is a reported private feeling offered in interviews belonging to the category of things a man says about his own life, rather than the category of things that can be confirmed by institutional documentation. Whether it is accurate in all its particulars is not something anyone outside Sullivan's experience could establish. What is in the record, alongside the 7 verified strikes, is the image of a man who carried water with him every morning because he had learned, through repetition, that the sky was not finished with him, who set a dented tin can on the passenger seat of his truck before each shift because 6 prior occasions had demonstrated that preparation, however modest, was better than its absence. who drove the same patrol routes and walked the same remote trail sections and continued to know the same park with the same detailed familiarity, even after the sky had found him in the ranger station and on the mountain road and on the open trail and at the fishing pond and in the truck with the storm visible in the mirrors. The Blue Ridge spread out in every direction from those patrol routes. The ridge lines caught weather in the morning and released it through the afternoon. The same updrafts that had always moved through the same valleys continued moving through them, building the same charge in the same clouds that had always formed above Shenandoah in summer. Sullivan knew all of it. He had known it for decades. He moved through it every working morning with a can of water on the seat beside him and the sky going about its ordinary, enormous business above the tree canopy, and he drove on. The Guinness file, when it was fully assembled, contained 7 separate medical reports and the supporting documentation that connected each report to a verified event. The file was a physical object, paper inside a folder, stored alongside the documentation of other record holders in other categories. It was an unremarkable object in its format and appearance. What distinguished it from other folders and other cabinets was only what was inside it: the 7 dates, the 7 mechanisms, the 7 injuries, and one name repeated at the top of each page, with the patient consistency of administrative fact. The file did not explain what the 7 events added up to. Files of that kind are not built to offer explanations. They are built to confirm, precisely and permanently, what occurred. Sullivan retired from the Park Service after his final strike. The patrol routes continued after him, walked and driven by other rangers who knew the same trails and the same ridge lines and the same storm patterns. The Blue Ridge continued producing its weather in the same way it always had. The transformer near the ranger station was still mounted on its pole near the wooden building. The fishing pond near Waynesboro reflected the same gray June skies it had reflected before Sullivan ever sat beside it with a rod in his hand. The world that had produced 7 documented lightning strikes across 35 years of one man's life continued without particular acknowledgement of what had happened in it. The file in the Guinness archive held what the world had done. It held the dates and the burns and the mechanisms and the witness reports, held them in plain institutional language without interpretation, held them in the way that carefully kept records hold things, quietly, indefinitely, without any need for the events themselves to continue in order for their documentation to persist. 7 reports, 5 decades, 1 name. Everything that had been verified was in there, and everything that had not been verified was not, and what was left, after the file was closed and returned to its place, was the specific patient permanence of things that have been carefully written down. Somewhere in the period between Sullivan's 6th and 7th strikes, on a morning that the record does not specifically document, he would have walked to his truck in the Park Service lot, opened the door, and set the can of water on the passenger seat before he started the engine. The morning might have been clear. It often was. The sky over the Blue Ridge is frequently clear in the early morning hours before the summer heat builds the afternoon cumulus on the ridgelines. A clear morning in Shenandoah has a particular quality of light, the kind that moves through the oak and hickory canopy in long horizontal bars, while the dew is still on the understory, and before the day has warmed enough to produce the haze that settles over the valley floors by mid-afternoon. He would have set the can down on the seat, not because the sky was threatening, but because it was the habit he had developed, and the habit that made the most straightforward sense given the specific and accumulated history of his mornings. The can rode there every day. It had become part of the arrangement of objects in his truck, the same way a radio or a thermos becomes part of the arrangement of a person's working day, familiar, expected, present by default, a practical object in a practical setting, doing the patient work of being ready. The truck would have moved out of the lot and onto the mountain road, the park spreading out in every direction from the pavement, the ridge lines visible above the canopy where the trail system opened onto exposed rock. Sullivan would have known each turn in the road with the ease of long repetition. The morning would have been ordinary. Here, most of his mornings had been ordinary, which is to say that the 7 extraordinary afternoons had arrived inside a life that was mostly built of ordinary mornings, ordinary patrols, ordinary paperwork, and the ordinary familiarity of a landscape known across a working lifetime. The can sat on the seat. The road moved under the truck. The sky, that morning, held nothing in particular, only the wide, pale, unconcerned blue of a Virginia mountain morning in the interval before the heat arrived and the clouds began to build and the day began its slow accumulation of whatever it was going to contain. On a hillside in Greece, somewhere in the region where the Aegean light falls at a low angle across limestone and dry grass, there is a patch of ground enclosed by a low stone wall. The wall is not tall. It is the kind of structure a person could step over without difficulty, built not to prevent entry through force, but to mark a boundary that people chose to respect. Inside the enclosure, the ground is ordinary, grass growing slowly back over burned earth, small stones settled into soil, the same insects moving through the same air as on the hillside outside. What distinguishes it is not anything visible. What distinguishes it is that lightning touched it once, and afterward the people who lived nearby understood that ground to be no longer fully theirs. The ancient Greeks called these enclosures abaton. The word carried the sense of a place not to be entered, not because it was unsafe in any practical way, but because it had been changed in kind. A bolt from the sky was understood as the direct physical contact of Zeus upon the world, not a symbol of divine attention, not a metaphor for power, but an actual touch, the way a hand leaves an impression on soft material. Ground that had been struck was ground the god had chosen. To enclose it was an act of acknowledgement, a way of marking the difference between the ordinary landscape and the place where something real had descended and briefly landed. The burned patch at the center of the enclosure grew over slowly with grass. The seasons came and went in their usual order across the hillside beyond the low stone wall, and the enclosure remained patient and set apart, its purpose requiring no further explanation. The Kuranos, the thunderbolt, was Zeus's primary weapon and his central symbol. It appears on coins, on temple friezes, in painted pottery found in sites across the ancient Mediterranean world, always rendered the same way, a winged shaft, symmetrical, blazing at both ends. The consistency of the image across centuries and across hundreds of separate artistic traditions suggests not a convention arbitrarily agreed upon, but something more like a felt truth, a visual fact that kept returning because it kept feeling accurate. Lightning looked like that. It moved like that. The civilizations around the Aegean looked at the sky during storms, recorded what they saw with whatever materials they had available, and arrived repeatedly at the same image. The Keranos was not invented. It was in some sense observed. Sites where lightning struck with particular frequency were treated as especially holy. The oracle at Dodona, one of the oldest in the Greek world, was associated with the sacred oak of Zeus and the storms that gathered regularly over the Epirus highlands. Priests and priestesses there interpreted the divine will through the rustling of oak leaves and the patterns of the weather, and a storm overhead was understood not as interference with the sacred work, but as part of it. The sky was not separate from the consultation, it was the consultation. What the Greeks were doing in their careful attention to struck ground and storm darkened sanctuaries was exactly what every culture that lived under open sky eventually did. They took the most powerful and least predictable thing in their visible world and found a place for it inside their largest explanations. Across the Norse world, the largest explanation belonged to Thor. His hammer, Mjolnir, generated lightning when he threw it, and the name itself may contain an echo of an older word meaning to grind or to crush. The sound of it, the physical fact of what lightning does to whatever it lands on. Thor was not a figure of abstraction. He was a very specific kind of god, loud, physical, direct, protective of farmers and ordinary people, and perpetually at war with the forces of chaos that threatened the structured world. Lightning, in the Norse understanding, was not indifferent to human beings. It was the sign that Thor was at work, fighting on behalf of the world that people depended on. Mjolnir-shaped amulets have been found across Scandinavia, in the graves of men and women, on Viking settlement sites in Britain, Iceland, and the eastern Baltic. They are small objects, most of them the kind of thing a person wears against the skin, not displayed. Iron, sometimes silver, worn smooth by handling over years. A person who wore a Mjolnir amulet was not simply performing a religious convention. They were carrying a specific piece of belief about the relationship between the sky and human safety, the idea that the storms were not hostile, but protective, that the lightning was wielded rather than random, that something enormous and powerful was in the weather above, and it meant them well. The amulets persisted in use for centuries through shifting political and religious landscapes, because the thing they addressed, the sound of thunder over a settlement, the brightness of a bolt crossing open sky, persisted without change. Mjolnir was also used to hallow. At weddings, at funerals, in the blessing of new land, the hammer was invoked, its shape made in gesture, or placed in image at the threshold of significant moments. This is a detail worth sitting with, quietly. A symbol drawn from lightning, the most violent and instantaneous thing in the weather, was understood as appropriate to the most solemn and tender events in a human life. The Norse did not separate the storm from the sacred. They used the storm to mark the sacred, the way a seal is pressed into wax to make something official and real. Farther west and north, across the forest and coastal peoples of the Pacific Northwest and the Great Lakes and the northern plains, the same sky produced different figures, but the movement of thought was recognizable. The thunderbird appears in the traditions of the Ojibwe, the Lakota, the Kwakwaka'wakw, the Haida, and many other nations, a vast raptor whose wing beats make the thunder, and whose eyes, or beak, or breath produce the lightning. The details vary by region and tradition, and the specific cosmological role of the thunderbird shifts considerably across different cultural contexts, but the core image holds steady across a remarkable geographic range, a bird immense beyond ordinary measure, in perpetual motion across the sky, engaged in a permanent conflict with forces below. On Kwakwaka'wakw totem poles, the thunderbird often appears at the apex, the highest point, the place nearest the sky. Its wings are spread, its eyes are wide and fixed. The carving does not depict a moment of action, but a condition of readiness, the permanent alert of a being that is always in the middle of its work. The cedar used for totem poles was chosen partly for its durability, its ability to hold form over decades of weather, and there is something fitting in that, the image of the storm being carved into wood that can survive storms, the permanence of the figure holding steady through the weather it represents. The thunderbird on a pole at the edge of a coastal village was not a record of a thing that happened once. It was a statement about a thing that continued to happen, a permanent presence acknowledged in permanent form. What all of these traditions shared was the same basic refusal. None of them looked at lightning and concluded it was merely a weather event, an accident of atmospheric electricity with no relationship to human meaning. Every culture that left records of its encounter with storms arrived, by different paths and through different cosmologies, at the same decision. The lightning was about something. It pointed towards something, or was the instrument of something, or was the embodied form of something that required acknowledgement. The specific theologies differed enormously. The impulse behind them was entirely consistent. This is not an impulse that requires apology or correction. It is one of the more remarkable things about the human encounter with the natural world that, confronted with the same set of electrical phenomena, without communication across oceans and millennia, people kept reaching for the same kinds of answers. The answers were different in content. They were the same in shape. Something vast and powerful is at work in the sky, and it is not indifferent to us. The Greeks said Zeus, the Norse said Thor, the Ojibwe said Anamiki. The specific names matter to the traditions that hold them. The shared architecture of the thought is something worth noting in itself. Benjamin Franklin stood in a field outside Philadelphia in the summer of 1752, holding a silk kite with a metal key attached to its string, watching a storm build over the Pennsylvania countryside. The experiment he performed that afternoon, or one closely like it, since the historical record of whether he performed it exactly as described is slightly murkier than the familiar image suggests, was among the most consequential in the history of natural philosophy. What Franklin was testing was a specific hypothesis that lightning was electrical in nature, the same phenomenon as the sparks produced in laboratory demonstrations with static electricity, simply operating at a different and almost inconceivable scale. He had already argued this in print. He had already proposed the lightning rod as a practical consequence. What the kite experiment did was provide direct experimental evidence that the storm cloud carried electrical charge, drawn down the wet string to the key, producing a spark that a person could feel. The implications were immediate. If lightning was electrical, then its behavior could be understood through the laws that governed electrical phenomena. It followed paths of least resistance. It sought connection with the ground. It could, in principle, be guided. The lightning rod, a pointed metal conductor mounted at the apex of a building and connected by wire to a ground plate, was already designed and already being installed before the kite experiment confirmed the theory it was built on. Franklin had reasoned his way to the solution before he had the conclusive evidence, and the evidence, when it came, was almost a formality. The rods went up on buildings in Philadelphia, then in Boston, then across the American colonies, and across England and France and the German states, and they worked, quietly and without ceremony, redirecting whatever arrived into the earth rather than through the structure it protected. The spread of the lightning rod was not without resistance. Some religious authorities argued that protecting buildings from lightning was an act of impiety, that if God chose to strike a place, it was not for human engineers to redirect the stroke. This argument was made sincerely by people who held, in a somewhat different form, the same basic position as the builders of the Greek Abaton, that lightning carried meaning, that it indicated divine intention, and that to intercept it was to interfere with something that ought to be received and acknowledged rather than deflected. Franklin's position, and eventually the position that won out through simple demonstrated efficacy, was that lightning was a natural phenomenon that could be managed like any other, and that managing it was not defiance of the divine, but rather the application of God-given human reason to a practical problem. The two positions argued past each other for decades. The lightning rods continued to do their work regardless. Franklin was not the first person to observe that pointed metal objects seemed to attract lightning, or to notice that lightning appeared to prefer the tallest object in a landscape. Farmers and shepherds, and anyone who had spent time outdoors during storms, had observed the same things without the theoretical framework to explain them. What Franklin provided was the framework, the understanding of charge, of conduction, of the path from cloud to ground, that turned an observed tendency into a manageable principle. He also, in the course of his investigations, coined or fixed the use of several words that are still in use: conductor, condenser, charge, discharge, battery. The language of electricity is in part his invention, assembled from Latin and English roots to name phenomena that had no adequate names before he described them. There is a particular figure in the history of European encounters with lightning who deserves more attention than he usually receives. George Christoph Lichtenberg was an 18th century German physicist, aphorist, and satirist, a person of remarkably broad intellectual range, who made contributions to optics, astronomy, and the study of atmospheric electricity. He is remembered today primarily for two things. One is the Lichtenberg figure, the branching electrical discharge pattern that appears in certain materials when they are struck by high voltage current, the same pattern that appears on the skin of lightning strike survivors as a temporary mark of the flashover. The other is a piece of research he conducted that was, in its quiet way, one of the more sobering natural experiments of the Enlightenment. Lichtenberg documented the practice of bell ringing during storms, the custom, widespread across Catholic and Lutheran Europe, of climbing into church towers and ringing the bells continuously when lightning threatened, in the belief that sacred sound would disperse or repel the bolt. The bells were inscribed with the phrase fulgura frango, I break the lightning bolts, and the inscription was understood not as metaphor but as functional description. The bells broke the lightning, the ringing kept the storm at bay. It was a technology of a particular kind, not mechanical, not chemical, but sonic and sacred, and it had been practiced for centuries before anyone thought to assess whether it worked. What Lichtenberg found was that over a period of 33 years in the 18th century, 386 bell ringers in Germany alone had been killed by lightning while ringing church bells during storms. The figure is not a rounding, it is a specific count drawn from documented records, the kind of meticulous German record-keeping that captured deaths in church registers and municipal reports across hundreds of parishes. 386 people, doing exactly the thing that was supposed to protect their communities from lightning, died because they were doing it. They were at the highest point of the tallest building in their village, holding a metal rope connected to a metal bell in an open tower during an electrical storm, and lightning found them with a regularity that, once counted, made the custom difficult to defend. This is not a story about foolishness. It is a story about the limits of available knowledge and the sincerity with which people acted within those limits. The bell ringers climbed their towers because they believed they were helping. The communities who sent them believed the same thing. The practice had the weight of centuries behind it, the authority of church endorsement, the testimony of local memory, all the things that make a belief feel solid and reliable. What it lacked was the kind of systematic empirical review that Lichtenberg applied when he went through the records. He was not trying to discredit religious practice. He He was a scientist who noticed a pattern in mortality data and followed it carefully to its source. The lightning rod changed all of this. It did not immediately eliminate bell ringing during storms. Old practices move slowly, especially when they carry religious meaning. But over the course of the later 18th and early 19th centuries, as lightning rods appeared on church towers across Europe, the deaths of bell ringers declined. Not because anyone issued an official ban, though some jurisdictions did eventually prohibit the practice for exactly the reasons Lichtenberg had identified, but because the rods were visibly demonstrably effective, and because effectiveness repeated often enough eventually revises even deeply held belief. The tower was protected, the bell could ring, the ringer could stay on the ground. The sacred sound, if someone still believed it mattered, continued. The dying stopped. There is a kind of continuity in all of this that is worth holding quietly for a moment. The Greeks built their enclosures around struck ground. The Norse wore their hammer amulets and invoked Mjolnir at the thresholds of important events. The thunderbird spread across the apex of poles, raised at the edges of coastal villages. Medieval Europeans climbed towers in storms and rang iron bells inscribed with the promise that the sound would protect them. Franklin stood in a field with a key on a string and drew the same spark down from the same sky, and concluded that what was needed was a pointed rod and a wire. All of them were responding to the same phenomenon, the same electrical process, the same return stroke, the same 30,000 Kelvin channel opening and closing in a fraction of a second above their heads. The phenomenon did not change. The human response to it accumulated, slowly, across thousands of years of observation, ceremony, experiment, and loss, until it arrived at a small copper rod mounted on a rooftop, doing its work without anyone needing to watch. The lightning rod is not a dramatic object. It does not look like much. A pointed metal spike, weathered and darkened by exposure, mounted at the highest point of a structure, with a wire running down the wall or along the edge of the roof to a copper plate buried in the earth below. On a clear day, it is nearly invisible against the sky. On a stormy day, it is simply there, doing nothing visible, conducting whatever arrives downward through the wire and into the ground at a speed and in a quantity that would have destroyed the building had it arrived without the rod. It performs its function without announcement, without ceremony, and in the vast majority of cases, without anyone being aware that anything has happened at all. A flash in the distance, a sound of thunder rolling across the rooftops, and then the storm moves on, and the building stands unchanged, and the rod darkens a little further with weather and age. In the centuries since Franklin's kite experiment, the lightning rod has been refined, but not fundamentally changed. The principle is the same principle Franklin identified in 1752. Point the conductor skyward, let the charge disperse gradually into the air, or let the return stroke run harmlessly to ground. Protect the structure between them. Modern versions use copper or aluminum, sometimes in continuous cable rather than discrete rods, sometimes in mesh configurations across flat roofs, occasionally in systems equipped with early warning sensors and remote monitoring. The physics have not changed. The math Franklin did not fully have but intuitively understood has since been worked out in detail and confirmed many times. The rod still does what he designed it to do, on buildings Franklin could not have imagined, in cities he never visited, in countries he never knew. The superstitions did not entirely disappear, of course. They were transformed rather than erased. People still say not to shelter under a tall tree in a storm, which is not a superstition at all, but a correct application of lightning physics. People still count the seconds between the flash and the thunder to estimate how far away the storm is, which is also correct. Sound travels roughly a mile every 5 seconds at sea level. The old caution about water and metal during storms has a basis in the same physics that Lichtenberg documented in bell ringers. Both create conductive paths that attract current. The practical wisdom survived even when the theological framing that originally carried it was set aside. The advice outlasted the explanation. There are places in the world where lightning is not an occasional visitor, but a permanent condition. The basin of Lake Maracaibo in northwestern Venezuela receives more lightning strikes per square kilometer than anywhere else on Earth. The Catatumbo River meets the lake there, and the warm moisture evaporating from the water collides with cold air descending from the Andes, producing electrical storms on roughly 160 nights per year, sometimes lasting 10 hours or more. The people who have lived along the lake for centuries call it Relampago del Catatumbo, the Catatumbo lightning, and it is so reliably present that historical accounts describe sailors using it as a navigational beacon, a fixed light in the sky by which they could locate their position at sea. Lightning, in this one specific place on Earth, performed the function of a lighthouse. The Catatumbo lightning has been estimated to produce roughly 1.5 million lightning strikes per year in that single basin. On clear nights, it is visible from hundreds of kilometers away, a silent strobe at the horizon, the cloud banks above the lake illuminated from inside in long pulses. Communities around the lake have grown up inside the rhythm of it. Children there grow up learning the sound of thunder, the way children in other climates learn the sound of rain, as a background fact of a particular kind of place, not alarming, not remarkable, simply present, the way the sky always is, doing what skies do. There is something restful about that image, not the lightning itself, though the Catatumbo lightning, seen at a distance on a calm night, is described by those who have watched it as one of the more quietly spectacular things the natural world produces. What is restful is the ordinariness of it, the way a phenomenon that would be remarkable anywhere else becomes, through familiarity and repetition, simply part of the texture of a place. The storms come on 160 nights a year. The lightning writes itself across the sky above the lake. The people who live there sleep. The same process of familiarization has happened everywhere that people live, under skies that produce regular electrical storms. The summer thunderstorms of the American Midwest, the monsoon lightning over the Deccan Plateau in India, the dry lightning of the Australian interior, all of them ordinary to the people for whom they are a regular feature of life, all of them extraordinary when encountered for the first time from the outside. Lightning is one of those phenomena that sits at the exact intersection of the common and the astonishing, so frequently occurring that it is a background fact of life across most of the inhabited world, and so physically extreme in the moment of its occurrence that it never quite loses its capacity to arrest attention. Franklin's lightning rod spread from Philadelphia to Europe within a decade of the kite experiment, and within that decade it had already become the subject of political argument. In France, the pointed rods Franklin recommended were adopted enthusiastically by scientists and natural philosophers who saw in them a symbol of enlightenment, rationalism, the application of reason to nature for practical human benefit.
Blunt rods, favored by some English natural philosophers who disagreed with Franklin's theoretical conclusions about the role of pointed condors, became associated with British scientific politics in the years leading up to the American Revolution. King George III, the story goes, ordered blunt rods installed at his palace after the American Association of Franklin's design became politically inconvenient.
Whether the story is exactly true in every detail, It reflects something real about the way even the most practical technology accumulates social meaning over time, a pointed rod or a blunt one. The storm did not care, but people did, for reasons that had nothing to do with the storm. That political dimension of the lightning rod faded as the rod's effectiveness became too obvious to argue with. It faded the way most arguments about technology eventually fade once the technology has been in use long enough that no one alive can remember the world without it. Today, the lightning rod is one of the most unremarkable objects in the built environment, invisible to most people, unmentioned except in technical specifications, doing its patient work at the top of structures from barns to skyscrapers without requiring any attention or ceremony from the people it protects. It is a thoroughly domesticated technology. Franklin's spark has become infrastructure, and yet the thing it manages has not changed at all. The stepped leader still descends in its invisible pulses through summer air, branching downward through 50-meter steps, pausing between each one. The return stroke still superheats its narrow channel to temperatures far beyond anything on the sun's surface. The thunder still arrives seconds later, rolling across whatever landscape received the bolt, fading into distance. The filterites still form in silence beneath the sand of struck beaches, glass tubes preserving the branching path of a bolt that passed in a fraction of a second, patient and permanent in the earth below. The Greeks were not wrong to notice that lightning was different from other weather. They were not wrong to think it required a response, an acknowledgement, a place set apart. The Norse were not wrong to connect it to protection. Lightning rods prove that the connection between lightning and safety is not absurd, only the mechanism was different from what they imagined. The bell ringers were not wrong to believe that the sound of bells was sacred and important. They were simply wrong about what the bells could do to an electrical storm, and Lichtenberg's count of 386 dead across 33 years is the record of that specific error, held without contempt in the same archive that holds everything else the 18th century learned about the sky. Every generation has been working on the same problem with the tools available to it.